Hello. In this video, we are going to derive the Boltzmann distribution using the principles of statistical thermodynamics. Let's take n identical systems. So our capital N here is the number of systems. And these systems have the property that each of them is identical. They have the exact same volume and they have the same number of molecules. And these systems are arranged in such a way that the molecules cannot escape from an individual system, but we do have flow of energy from one system to the other through these walls. So they are identical, they're distinguishable, so we can say this is the first system, this is the second system, third system, for example. So we can distinguish the systems. Each system is otherwise identical in having the exact same volume and the same number of molecules inside it, but we are allowed to have energy flow from one system to the next. So we call this collection of n systems that are identical but distinguishable, each of which has the same volume, the same number of molecules, and we can have energy flow between the systems. We call this collection a canonical ensemble. In statistical thermodynamics, there are a number of different and important ensembles, and this is the first one that we're going to investigate, the canonical ensemble. Since energy is free to flow between the systems, all the systems will not have the exact same energy. They will have different energy levels. So we need to keep track of how many of these systems have a particular energy. So we're going to use the symbol of a small n, and we're going to write it with a different color just to avoid confusing ourselves with the capital N in purple, which is the total number of systems. So n sub 1, with a small n, is the number of these systems that have the energy level, the first energy level. Then, as we might expect, n sub 2 is the number of systems that have energy level 2. And just to kind of show us, then n sub 3 is the number of these systems that have the third energy level. So notice we add up all of these number of states that we have, starting from the very first energy level, going up to however many there are. So if we add up n sub j, this total has to equal our capital N, because each of these particular systems has to be in some particular energy level. When we add up all the energy levels, we get the total number of systems in our ensemble. So we have, and we're going to use this relationship quite a bit later on, but here we have the sum over the n sub j's equals capital purple N. We have a second important relationship. Recall that each of these sets of systems that all have a particular energy. So the ones that have the first level of energy we call n sub 1. Well, its actual magnitude of energy, we'll use the symbol E sub j. So this is the number of systems that have the energy of the jth level, and then the energy of the jth level itself is going to be E sub j. So if we multiply the number of systems that have a particular energy by its energy, and then we sum this up, what we get over this is the total energy of the entire system. Which again, we'll put in a slightly different color here, just to distinguish the total energy from the energy of a particular energy level. And an important thing to see here is that this is going to be a constant. So we have the law of conservation of energy that we're going to impose on our canonical ensemble. So we'll see that these two particular sets of summations are important restrictions on our canonical ensemble. The first is that each of the systems has some particular energy level, so if we sum over all the levels, we get the total number of systems. And the second relationship here, the second summation, tells us that if we sum up the energies of each of the systems, we're going to get the total energy of the system, which is going to be a constant. As we might imagine, there can be many different ways of arranging the energy among these identical systems such that the total energy remains constant. So the symbol that we're going to use for the number of different ways of distributing energy throughout these systems, we're going to use the symbol omega. So we may have seen this before in discussions of entropy and also in evaluating the number of microstates for electron term symbols. So using the principles of probability, we know that the way we can calculate how many different possible distributions we have is we have the total number of systems, n factorial, and this is then divided by the number of systems that are in the first state, factorial, times the number that are in the second state, factorial, and this is going to go up however many as we have. Let's put n sub j, factorial. So when we evaluate this, this will give us the number of different ways of distributing the energy among these various different energy levels. Next, we're going to apply a principle from probability and statistical mechanics that the more likely, the more different ways we have of realizing a distribution, the more probable it is. So what we want to do in principle is find out in such a way as we maximize this omega, maximize the number of possible ways of realizing this distribution. Now it turns out, mathematically, that is not the easiest way to achieve what we want to do. So we're going to do something that works similarly to maximizing omega. And that is, we're going to maximize not omega itself, but the natural logarithm of omega. And this is going to work as legitimate because the natural log of omega is a monotonic function, monotonic increasing function of omega. Since omega is a positive integer, as omega gets bigger, the natural log of omega gets bigger as well. So if we maximize the natural log of omega, in the process, we are maximizing omega itself. One mathematical technique that we're going to make use of here is Stirling's approximation. So we have a way of approximating the natural log of n factorial when n is a very large number. And we approximate it as n times the natural log of n minus n. And this is particularly legitimate in the case of statistical thermodynamics because the number of systems that we're talking about, the number of particles that's involved in a typical macroscopic system, is so astronomically large that these statistical approximations that we make tend to be overwhelmingly effective. So it's not like a small system where we only have a few particles. We have, even in the smallest chemical system that you can see with your eyes, has such a vast number of particles that it's legitimate for us to rely on an approximation such as this version of Stirling's approximation. If you look in mathematical textbooks, there are a number of different versions of Stirling's approximation, and this is a particularly convenient one that we're going to use for our particular purposes. So recall our expression for the number of ways of achieving our distribution, omega, and then recall also that as a way of maximizing this particular function, what we're first actually going to maximize is the natural log of omega. So based upon our expression for omega, we can write down, using the properties of logarithms, an expression for the natural log of omega. So recall that when we have a division, that if we have a over b, the natural log of a over b is the natural log of a minus the natural log of b. So this gives us the numerator, the natural log of big N factorial, and minus the natural log of n sub 1 factorial plus the natural log of n sub 2 factorial, and going up to the natural log of n sub j factorial. So here we're able to achieve a couple of very useful things in that we're able to convert the omega into the natural log of omega, but in the process we've turned what is a division problem and a multiplication problem into an addition and subtraction problem. So that now we have a expression for the natural log of omega in terms of capital N and then these small n sub 1, n sub 2, n sub j's. Since this expression now has turned into a sum, we can write it with summation notation to make it take up a little less space. Now we have n sub j factorial, the sum. Now we can apply Stirling's approximation for the natural log of capital N factorial. So that's going to be n times the natural log of n minus n. And then we have our, that's for this particular expression in purple. And then we have our summation, j equals 1 over the small n sub j's. So this is the expression, at least for now, that we're going to try to maximize. And remember, from calculus, we can determine when we have a relative maximum or minimum, and we're going to have a maximum when the derivative of this expression with respect to every single variable, every single n sub j, is going to be equal to 0. So we convert this particular equation, or a version of it, which we're going to see in a second, into a series of equations where we're going to take the derivative of this expression and set it equal to 0. So by calculus, in principle, what we want to do is take the partial derivative of the natural log of omega, the number of ways of realizing this distribution, with respect to each of the individual n sub j's, and we're going to set each of these equal to 0. But we have one small problem. So that's entirely true, but we have one other thing to keep in mind. We have two constraints on our system. So we have 2 degrees of freedom that we have to remove. The first of them comes about because when we add up all these n sub 1, n sub 2s, and n sub whatevers, it has to equal capital N. So the total number of systems doesn't change. So that's a restriction on the system. The second restriction on the system is that the total energy of the system can't change. Remember, it's a constant. So when we perform our calculus techniques, we have to somehow bring those two constraints in addition to solving each of these individual equations. And there's a particular technique called Lagrange's method of undetermined multipliers, which will allow us to solve this system of equations but also satisfy the two external constraints that we have in the canonical ensemble. This subscript j here is just a dummy variable, so for purposes we're going to need in a second, let's change this from j to k, because we're going to be using j as a distinct subscript and we don't want to get them confused. So same principle applies. We're going to go through each of the different possible n's and take the partial derivative with respect to that variable and set the expression equal to 0. We have to modify each of our derivatives here, change the operand from simply the natural log of omega to add these two new expressions. And this first expression, including the parameter alpha, accounts for the fact that the total number of systems has to equal capital N. So that's the first restriction, is imposed by adding this particular term to every single one of these derivatives. The second expression, where we have beta, and this involves the total energy of the system. So this accounts for the fact that the total energy of the system cannot change. So the way that we can maximize the natural log of omega, but subject to the two constraints, is by means of this particular expression using the undetermined multipliers alpha and beta. If we had more restrictions, then we would have to have gamma delta, for example. So going from here to here is somewhat complicated, but we need to do that to account for the two restrictions on our system. Now, to find these particular partial derivatives with respect to n sub k, we are going to, for the sake of clarity, we're first just going to find the partial derivatives with respect to the natural log of omega, and then we're going to do it with respect to the second and third terms. So we can simply write down the first part that we're going to solve here. So we have the partial derivatives with respect to the n sub k's of just the natural log of omega. And then what we want to do is we want to replace natural log of omega with the expression that we had already worked out for natural log of omega in the case of the canonical ensemble. So what does that give us? Well, it gives us the natural log of big N factorial. I'm going to put it in purple again to remind us that that's our big N, and it's minus the sum of the natural log of the small n sub j's. So now that we've replaced the natural log of omega with this particular expression, which is true for the canonical ensemble, we're going to do a trick. And we're going to use the same trick twice. And the trick is the Stirling's approximation that we had seen already. So first we're going to use Stirling's approximation for the natural log of big N factorial, and then use it for the summation here of the natural log of the little n sub j's factorials. So first let's write out for this particular expression, and recall that Stirling's approximation here is going to be n times the natural log of big N minus n. So these two expressions are Stirling's approximation for the natural log of big N factorial. Secondly, now we're going to have Stirling's approximation for the natural log of little n sub j factorial. So again, we have our summation j equals 1, and now we have little n sub j times the natural log of n sub j minus n sub j. The advantage of Stirling's approximation in each of these cases is now that we had an expression that had a factorial here and a factorial here, and now we have expressions that have no factorials at all. So now we have 4 terms. But we notice something here. Here we have capital N, purple. And recall that if we take the sum from j equals 1 over all the possible levels of the little n's, these add together to be big N. So here we have a minus n minus a minus. The summation of this is going to be plus n. So this term and this term will cancel. So this simplifies, such as it is, to n times the natural log of big N and then minus, and then we have the sum, j equals 1 over natural n sub j times the natural log of n sub j. So notice that we haven't found the derivatives yet, but we've simplified the expression for the natural log of omega. Now for the derivative of big N times the natural log of big N. We realize that we have the derivative of a product. So our first function we'll call big N, and our second function will be the natural log of big N. So recall from our product rule that it's the first times the derivative of the second function, and the derivative of the natural log of n is simply 1 over n, plus the second function times the derivative of the first. So the second function is the natural log of big N. And now the derivative of big N with respect to the little n's is, remember that big N is n1 plus n2 plus n plus 3, and so on. So the derivative of big N is going to be 0 with respect to every single one of the n sub k's, except for where, so for example, with respect to n sub 1, the plus n sub 2, n sub 3, n sub 4 part will all be 0, but this also includes n sub 1. So with respect to n sub k is always one of the terms inside big N. Its derivative with respect to that particular variable is going to be 1. For all the other n sub somethings that are not n sub k, the derivative is 0. So this turns out to be 1. So we see here that we also know n times 1 over n is going to give us a value of plus 1. So it's a very complicated way of saying that the derivative of big N times the natural log of n with respect to any single one of these n sub k's is always going to be the natural log of big N plus 1. To find the derivative of the second part of this term, the second term here, the n sub j times the natural log of n sub j, we use almost exactly the same reasoning that we use for the big N natural log of big N. Because if we have any n sub j that is not equal to n sub k, the derivative is going to be equal to 0. So this is only important when the j index here is exactly the same as the k index. So the nice thing about this particular expression is that even though we started with a sum, all the terms of this sum drop out except when j is equal to k. So in the process of taking the derivative, we're going to lose the summation sign, which is helpful. And then similarly, when j is equal to k, we get the same kind of derivative that we got for the big purple n. So we would end up getting n sub k times 1 over n sub k plus the natural log of n sub k. And since n sub k times 1 over n sub k is simply equal to 1, that's going to give us that we have natural log of n sub k plus 1. So substituting into the derivative for the natural log of omega, we find that it's going to be equal to the natural log of big N plus 1 minus the natural log of n sub k plus 1. So now the 1's are going to cancel here, so we get that this is equal to the natural log of big N minus the natural log of little n sub k. And we can actually use the properties of logarithms to write this more succinctly as minus the natural log of little n sub k over big N. So after all this work, we've still found the derivative of the natural log of omega part. We still have those two more terms to work on. So here are the second and third terms from our complicated expression in those derivatives that we had set equal to 0. So let's see what the derivatives with respect to n sub k are in each case. And again, because of the way the derivatives work, that any time j is not equal to k, the derivative is going to be equal to 0. So that's the nature of partial derivatives. So the effect of taking these partial derivatives for the second and third terms are going to be that we are going to get rid of the summation sign. So the derivative of n sub j with respect to n sub k, if j and k are equal, is simply equal to 1. So we have a constant times 1, so that's going to give us minus alpha. Similarly, we have minus beta n sub j times e sub j. Anytime the j's are not equal to k, the derivatives here is going to be equal to 0, so they all drop out. And the only time we have to worry about finding the derivative is when j is equal to k. So that's going to give us minus beta times the energy sub k. So all the steps we've done so far in working out the derivatives gave us that derivative was the natural log of n sub k divided by big N, and we have our minus alpha minus beta times the energy sub k. And the reason we did all this was using the fact that the derivative is equal to 0 at a relative maximum. So we set all this equal to 0, and now we're going to be able to solve for the ratio of the natural log of k to the big N. So let's multiply this expression by minus 1, because minus 1 times 0 still gives us 0, and then add a minus alpha and minus beta e sub k to each side. So that's going to give us the natural log of n sub k divided by big N is equal to minus alpha minus beta the energy sub k. Now we raise the left and right sides as powers of e and use the property that e to the natural log of x is simply equal to x. And that gives us the ratio of n sub k to big N is equal to e to the minus alpha minus beta e sub k. We are going to use this expression further as is in a second, but let's also do a manipulation on this particular expression, multiplying each side by the big N. So that gives us that n sub k is equal to our big N times e to the minus alpha minus beta times e sub k. And the reason why we want to do this is that we are now going to sum over all k's on each side here. You notice that if we sum all the little n sub k, we simply get big N. So let's do that right here. Next, let's break this sum of the exponentials and rewrite e to the minus alpha minus beta e sub k as two different exponentials. Notice that e to the minus alpha does not include anything that has a k subscript. So therefore, this is simply a constant. So we can write the right-hand side as minus our big N e to the minus alpha. Now this term over here has the e sub k's, so since it does depend upon k, we have to leave that as a summation. Now we divide each side through by n, we have n on each side, and then divide each side by the sum of e to the minus beta times e sub k, and this will give us an expression for e to the minus alpha, which is going to give us 1 over the sum of e to the minus beta e sub k. This quantity in the denominator, the sum of e to the minus beta times e sub k, we call the canonical ensemble partition function, and we give it the symbol q. So e to the minus alpha is equal to 1 over our big Q. And now we're finally ready, after much work, to substitute this expression into the expression we had worked out before for the number of systems of a particular energy out of all the possible systems. So this n sub k divided by big N is the probability that we will have a system with a particular energy E sub k. So that gives us the probability that a system will be in a particular state k is equal to our n sub k divided by our big N here. And we saw that this is going to be equal to e to the minus beta times energy E sub k divided by the canonical ensemble partition function Q, which is equal, and we'll write this out explicitly what this is, the sum over all the k's of e to the minus b e sub k. And this particular relationship here is what we call the Boltzmann distribution. And there's one more thing we can do here, which we're not show the derivation of it, but is we can get from other results, is the evaluation of beta. It's going to turn out that beta is simply equal to 1 over k times t, where k in this case is not the index k, but it's the Boltzmann constant, so I might write it as k sub b and T is the thermodynamic temperature. I thank you very much for your attention for this very, very long derivation. As always, have a good one.